In this data, we have, of course, again, our heating cost data, but this time, in addition to temperature and cost, we are adding in insulation and age. And we want to see, can the average outside temperature, insulation level, and age of a home predict the cost to heat that home? So I went ahead and used all of these variables, of course cost being my y, what we're predicting, and the temperature, age, and insulation being my x's, and ran the regression. Here are the values that I got. The first thing we look at is this significance f, which is our global p-value. If it's less than 0.05 or 5%, then at least one of our variables is going to be significant. Then you have to go down and look at each of those variables, temperature, insulation, and age, look at their p-values and see if those are less than 5%. If they are, then they are significant and they get kept. If they are not, in the stepwise elimination method that we use, you always remove the highest non-significant variable. In this case, there only is one, but if there was more than one, you would remove the highest, just a single one, and run the regression again. And keep running the regression until all of the variables are significant, removing only the highest non-significant variable each time. So in this case, I removed age because it's over 5%. I reran the regression analysis, eliminating age, so I just have temperature and insulation. I know at least one of those is significant because my global p says so. And now I look at my individual p-values, and the p-value for temperature is 3.43 times e to the 10th, which means I'm going to move that decimal place to the left, so it's going to be a really small number. And here I have another small number. Again, if you want to change these into percentages to make them easier to compare, feel free. So this one is so small it's less than 0%, and which we would mark as less than 0.001, and this one is 0.11%. So again, very, very small. So what does this mean? Well, let's interpret the results. Is temperature a significant predictor of cost? Remember, significant has to be less than 0.05, which means there's a significant chance that you are not wrong. And you want that to be really small. So it has to be less than 0.05. Is temperature a significant predictor? Well, it made it in here at less than 0.05, so yes, it is. Is insulation? Insulation was at 0.11%, so yes, that is also. And we had to remove age, so age is not a significant predictor of cost. So when you actually go to do the predictions, ignore it. It's not applicable. All right, so what if the temperature is 50 degrees and the insulation level is 6? Remember, that's the point of doing all of this, is to take the information you have and try to make future predictions. Well, I can't make a nice scatter plot because it would plot the lines as individual series. And really, we want to see how temperature and insulation together impact cost. Can we use those variables together and predict what the costs are going to be? Well, we can, but it's just not that easy to graph. So we're going to come back to our regression equation. And this time we have the intercept. Again, we always start with the intercept. And then we're going to add to that. In this case, it says temperature is 50 degrees, so 50 times the coefficient for temperature. And this time we have a second variable that's significant, so then we're going to add to that a level 6 insulation and multiply that by the insulation coefficient. So you are always taking the intercept and then adding variable 1, whatever that is, the variable 1 value times the variable 1 coefficient, and then the variable 2 value times the variable 2 coefficient. However many are significant, you'll do that for each of those variables. And we can see that if the temperature is 50 degrees and the insulation level is 6, we would expect the cost to heat the home to be about $145. Now, if the insulation level goes up by 1 level, what happens to the cost? We could put this all in a formula again, but let's not. Let's just talk through it. If the insulation goes up by 1 level, so if this insulation goes up by 1, we expect the cost to go down by $13.03. That's all that's saying. So each time there's a change of one difference in this, one difference in the variable, 1 degree in temperature in this case, we would expect the cost to go down, because it's negative, by $4.83. Now I accidentally skipped one. What if we ignore the variables? What if they're 0? If the variables are 0, then all we have left is the intercept, because anything multiplied by 0 is going to be 0. So if we ignore the variables, this is where it's going to cross the y-axis at the intercept. And I'll put this one in here too. If the insulation level goes up by 1, that was a negative 13. We expect the cost to go down by $13. Now, how much of an impact in prediction does temperature, should be temperature and insulation. So do both variables together, how much do those have an impact on what the prediction is going to be? How closely can we use that to predict? And that is our adjusted R-square. When you're doing simple linear regression, you use R-square. When you have multiple variables, you use adjusted R-square. And this is simply saying that we can say that if the cost goes up or down, it's based on 77% of that value is based on the changes in temperature and the changes in the insulation. And that is a percentage that goes from 0 to 100%. So 78% of the change in cost is based on temperature and insulation. Now this is great because when we did simple linear regression and we had our R squared, approximately 69% comes from temperature. And now we're adding in another variable, and now instead of that 16, now we have all the way up to 78%. And we know that it comes from temperature and insulation. So temperature is the biggie, and then insulation adds even more impact for how closely we can predict the actual value. Now, what is the average distance between the predicted cost and the actual cost? So remember, if we could plot this along a line, and we had that line of best fit, how far away would those data points be from that line? And that's simply our standard error. And that's very similar to the last question, just worded a little bit differently. On average, how much error are our predicted values likely to have? And that is also going to give us our standard error.